Okay, in this example, in this video, we're going to be looking at inverses of relation. Relations are ordered pairs consisting of x, y, relating one value to the other, the inverse of which is all ordered pairs y, x. Essentially, a way of remembering it is that x and y kind of flip-flops compared to the original to the inverse. The domain of the inverse becomes the range of the original, and the range of the inverse becomes the domain of the original. The inverse is denoted with this notation, f-1. Now, be careful not to mix this up with an exponent, because a to the negative first as an exponent means 1 over a to the first. Whenever it comes to being applied to functions, it represents the inverse. So this notation means inverse and not the reciprocal. Similarly, sine -1 would be the inverse of sine, which you talk about in trig. That's one of the most common examples that comes to mind. Also, as a reminder before we start, the definition of a function, which is talked about throughout the different examples, is that a function is a relation where each x value has only one y partner. So each x has only one y value. Now the y values can have more than one x value associated, but each x can only have one y partner. So in this example, we're finding the inverse of each, and we're supposed to determine the inverse if the inverse is a function or not. So if we look at a here, a is originally a function. You can see that none of the x values repeat, so the original is a function. We're not actually asked about that. That's just a bit of a side note. The inverse, however, if we go and find the inverse, well, inverse when it comes to ordered pairs literally just is switching x and y. Nothing too complicated with that. Switching x and y for each of our ordered pairs. Okay, so this is the inverse of the relation. Now to check to see if the inverse is a function, let's check those x values. We have no x values that are repeating, therefore each x value only has one y partner. So the inverse is a function. And so is the original, which means this is what's called a one-to-one function, which we will see in later down the road. But it just means that each x has only one y partner, and each y has only one x partner. If we take a look at b here, you can see that this x occurs more than once with a different y value. So the original is not a function, but again, we're not actually asked about that. That's just a bit of a side note. If we take a look at the inverse, though, which is what we're actually looking at, switching the x and y values here. So 6 and 1, 6 and 3, and 9 and 4. If we check this out, you can see that the x value is repeating and it has a different y value associated with it. Therefore, this inverse is not a function. And there we go. So in this example, we're going to find the inverse of f of x equals 3x minus 2. Now, the way I usually start this off is I remind people that f of x is really just y. And to find the inverse, just like with the ordered pairs, we start by switching x and y's location. So it really starts off as y equals 3x minus 2. So when I go to find the inverse, I switch it to x equals 3y minus 2. And traditionally, you do need to get y back by itself. So we're going to add 2 to both sides. Get x plus 2 equals 3y. And then we'll divide both sides by 3. We can't actually do any of these operations, so it's going to stay x plus 2 all over 3. Now there are a bunch of different equivalent forms that we could write. We could write it as f of x, oh, sorry, not f of x, because we're representing an inverse. We want f inverse of x. That just denotes that this is the inverse of the function f. X plus 2 over 3. We could also write the expression on the right as x over 3 plus 2 over 3, dividing each term individually by 3. We could also write the fraction x over 3 as 1/3 x plus 2/3. All of these are correct, and you can also use either the f inverse notation or the y equals notation with any of them. So there's many different ways of representing the final answer. It just depends on what you're asked. In some cases, breaking it up like this is nice, especially if you can reduce this fraction. We can't in this case, so we'll just leave it as is. But any of these versions would work. Okay, in this example, we're going to be finding f negative 1, which again, this is the notation that says the inverse of f. So we're going to be finding the inverse of the function f of x, which is equal to the square root of 2x plus 5. Now remember, when we start by doing this, f of x is really just y. And to start finding the inverse, we will switch x and y. So instead of y equals, we'll have x equals the square root of 2y plus 5. You may see this note over here. This is more just a note for me whenever I'm teaching in the classroom, just because I tend to not carry notes around with me, and I sometimes forget because I'm old and senile. But anyways, back to this part for now. We'll take care of the note over there later. So as I go through this, I need to get y back by itself. So I'll get rid of anything outside the radical first, and there is nothing. So I will start by squaring both sides. So we'll have x squared equals, squaring and square root will cancel, 2y plus 5. Then we'll get rid of addition and subtraction. So subtracting 5 on both sides. So we'll have x squared minus 5 equals 2y. Then just one more thing to get y by itself, dividing both sides by 2. So we'll have y equals x squared minus 5 over 2, or f negative 1 of x equals x squared minus 5 over 2. Now, if this 5 was actually divisible by the 2, I would probably break it up into two separate fractions and simplify that. But since it isn't, this is probably the preferred answer. Now let's talk about that domain range note I have over here. Now this original function is a square root function. The square root function looks kind of like this. We'd be moving over here like that, something like that. This function that we have for the inverse currently, let's see, it'll probably be something like this. You notice that the shape is not exactly the same. While they both have the same U shape, the quadratic doesn't have both pieces of the U shape. So we have to restrict the domain of this inverse, this quadratic function, to match up with our square root function. So in order to do that, since the domain of the inverse, which is what we need to restrict, corresponds to the range of the original, we'll look at the range of the original, which is going to be y greater than or equal to 0. If we use our transformations, there's no addition, subtraction, or anything outside, so it will have the same range as the basic function. And if we switch x and y in our range, it is going to become, for the inverse, in x, which will be a domain of x greater than or equal to 0. Because remember, the inverse and the original, the x's and y switched places. So the range of the original is the domain of the inverse, which is what we use to restrict a portion of the graph. But there we have the complete answer, making sure that we're only using half the U-shape and not the full U-shape. Okay, in this example, we're going to find the inverse of y equals x squared plus 5, and then we're going to spend some time talking about the domain and range of the original and the inverse. So let's go ahead and find the inverse first. We're going to start off by switching x and y. So we start off with y equals, and then to find the inverse, we'll switch it to x equals. Instead of x squared, we're going to have y squared plus 5. Now we're just going to walk through and try to get y by itself. So I'll get rid of addition and subtraction here first. Subtracting 5 on both sides. And we'll have x minus 5 equals y squared. Now, according to one of the properties, if we have y squared equal to something, then y would just equal the plus or minus the square root. A lot of people refer to it as square rooting both sides here. But that will result in us having y equals the square root of x minus 5. Now, remember that if we are applying that property where we're square rooting both sides there to get rid of the squaring, we would need to make sure we have both positive and negative because there are two possibilities. But that brings us into our note about domain and range. So the original function, so my original, and by the way, this is the rewritten equation. So the original function, y equals, and I forgot to switch back to my markers, y equals x squared plus 5. Might look something like this, and it does look something like this. I'm just not putting the tick marks. And it has a domain of all real numbers and a range of y greater than or equal to 5, just using transformations. After doing the inverse, so this is my inverse, which is going to be graphed here, we actually get a radical equation that has both the plus or minus, where we have a transformed version. I don't know why I'm putting the tick marks on this one, but not the other one. We have the graph like this. However, this right here isn't actually a function. The combined plus minus doesn't actually create a function. The plus creates the top half of this u, this sideways u, while the minus sign creates the bottom half. But if this is as one function or one expression, it would fail the vertical line test, making it not a function. So in some cases, we weren't actually asked about functions here, but in some cases, you may see them restricted the original function. So for example, if they gave us this as the original function with x being greater than or equal to 0, then as I go through and do it, we would be getting y equals, for the square root, still x minus 5, but we wouldn't have to pose a restriction on it because that restriction would actually correspond to whether we're using the positive or negative. The positive sign being the positive x values, in this case, not always, but in this case, and the negative sign being the negative x values. So if we were giving this as the original restricted expression, then this would be its corresponding inverse. And likewise, if we had y equals x squared plus 5, when we have x is less than or equal to 0, then instead of using the positive radical, we would be using the negative radical. Because the negative radical would correspond to, for the original function, the value is less than 0, in this case, depending on the transformations, this might be different. And the right side would correspond to the positive radical version. And that's the summary with all the notes. In this case, we didn't have to worry about the restrictions because they didn't impose the original restriction. So we didn't have to worry about our final answer being a function or not. But this is the summary. And this, overall, what we have here is actually the answer given the question that we had, making sure to have both the plus and minus given the question that we had. I have no clue where that paused. so I'm just going to say that again. But this highlighted in green is the answer for the question that we're given. But we did discuss the different scenarios if we had a restricted version of the original equation, which might be used for things like calculus. So the next part we're going to look at is graphs, and a function has an inverse if and only, a function's inverse is a function if and only if it's a one-to-one function, meaning each x has exactly one y and each y has exactly one x. There is an example of a one-to-one function in the first example with the order pairs. Now, as far as the next part here, horizontal line test and the vertical line test are similar. The horizontal line test tests to see if its inverse is a function. Not a function. Because the horizontal line test here hits the function in more than one spot, its inverse would not be a function. The original is a function because no matter what vertical lines I try to draw here, it's only ever going to hit the graph one time. Therefore, the original is a function based on this quick little example. And a one-to-one function has both the original and the inverse being a function, meaning that it passes both the horizontal and vertical line tests. Let's take a look at the examples here. We're supposed to determine if the graphs have functions that are inverses and then sketch the inverses. This is regardless of whether they are functions or not. So let's just talk about the original and inverse. Why not? So I'm going to add some words. Oops. Why not talk about both of them? Okay, so the original, if we look at the original, no matter how many vertical lines I draw, it's only going to hit once. This is essentially the example I had just given. So the original is a function. But like the example I gave where I was talking about the definitions, if we look at a horizontal line test, it would hit twice, meaning that the inverse is not a function. We're also going to sketch the graph. It's pretty simple to do this. We just take some points, like 0, 0 here. Since we don't have an equation, we're just going to use some points. The inverse of 0, 0 would be 0, 0. That one's kind of boring. I can use this one as well. The inverse of negative 1, 1 would be 1, negative 1. So that would put it 1, negative 1 down here. Another point I might use is 1, 1. But the inverse of 1, 1 is just 1, 1, switching the x and y values. So those are the typical points I typically use whenever I deal with transformations and stuff. But that doesn't really help us for this inverse expression. So I'm going to pick up this point so I can help myself get the shape a little better. That point is negative 2, 4. So the inverse would be 4 comma negative 2. So 4, negative 2 right there. And then the same thing for this point up here. It is 2, 4. So the inverse is 4, 2. So if I plot that, there we go, and draw it in. So there is the inverse. The next one here is, well, if we look at the original, no matter what line I draw, it only ever touches once. So the original is a function. And if I do a horizontal line, same thing happens. So the inverse is the function. So this is a one-to-one function. To sketch the inverse, I'm just going to pick some points. I think I'll use this one. This is -1, -1. The inverse of that is still -1, -1. So I'm still in the same spot. Let's use this one as my other one. 1, 3. The inverse of that will become 3, 1, just switching my x and y values. You only need 2 points to graph a line, so we had the blue point, which didn't move when I talked about the inverse, and the red point, so there we go. Now, before I end this example, there's one more key concept to look at. If you look at these graphs closely, the inverse in its original is actually a reflection across a specific line. That line is the line y equals x, which will come in handy when we try to verify inverses. Okay, this next portion is going to look at the identity function and the definition of what it actually means to be inverses. So the identity function is the function I of x, it's often referred to as I of x, equals x. So the identity function, what that is if we plug in x, we get out x. It makes no changes to what you plug in. It's the most basic identity there is for functions. This is similar for the multiplicative identity, 1, because if you multiply by 1, it doesn't change anything. And if you add 0, 0 is the additive identity. So these are identities for basic math. 1 is the multiplicative, while 0 is the additive. Now, something that's nice and handy is that when we're talking about identities, we use that often when we're solving equations. For example, if we have 2x plus 5, the opposite of this plus 5 is a minus 5. They cancel out and form the identity 0. Well, adding 0 doesn't do anything, and that's what makes it the identity. It doesn't change the actual value. Just like x, this function, this identity function, doesn't change what happens to x. It just stays x. It doesn't do anything to it. Same thing with 0. Adding 0 doesn't change the value of an expression. That's what makes it the identity. Same thing with multiplying by 1. That's what makes it the multiplicative identity. It doesn't do anything. But in all these instances, in terms of basic math, there's always something that can cancel out and form the identity. Positive 5 and negative 5 added together cancel out and form the identity 0, the additive identity. While 2 times its inverse, multiplicative inverse, 1/2, would cancel out and form the identity 1, the multiplicative identity. So what, therefore, does inverses actually do for functions? Well, the inverses for functions essentially cancel out the function. And it's not erasing, so I'm just going to have to ignore it and move on. So the inverses here of functions cancel out and form this identity. So if I have a function and I try to do the composition, so f of g, and that's equal to x, then these two could be identities. However, since composition is not transitive, meaning not commutative, that means it may not be the same the other way around. So not only do I have to verify that f of g is equal to x, but also have to make sure that g of f equals x. Because just because one of them simplifies to be x doesn't mean they both will, because it's not transitive. I keep saying transitive. Sorry, it's not commutative. The order actually matters for composition as far as which one is outside. And if two functions are inverses, they will cancel out and form the identity. Just like if two numbers are inverses, they will cancel out and form the identity. 0 if we're talking about adding and subtracting, or 1 if we're talking about multiplication and division. Okay, so in this final example, we are going to be verifying that the function f of x and the function g of x given here, the 4x minus 3 and the x plus 3, the sum of x plus 3 divided by 4, are inverses of each other. Now, we're going to do this by using the definition of inverses, meaning that if we do the composition of f with g and g with f, that looks too much like a multiplication dot, so I need to change that. So if we do both of these compositions, and they both simplify to be the identity function x, then these two functions are inverses. Remember with verify is a way to, or a word that means to prove, which means if you are doing this for the purpose of a course, every step would be the answer. Verifying is showing that it's true, so you got to show it instead of just skipping through all the individual steps. So if I set this up, f would be my outside. It means f of g of x. So f is my outside function. So 4 parentheses minus 3 instead of 4x minus 3. My inside one will be the x plus 3 all over 4. Here, we're multiplying a fraction times a fraction, and we have a 4 on top, 4 on the bottom, connected by multiplication only, so they will cancel, leaving me with just x plus 3, and my minus 3 comes along. Positive 3 and negative 3 cancel out, leaving me with just x. So far, one of them does equal x. Now, in order for them to be inverses, both compositions has to simplify to be the identity function x. So let's check the other one. The other one is g of f of x. So if we do this, go through my outside one, replace x with parentheses. So we have x plus 3 over 4. So we're going to put parentheses plus 3 over 4. Then inside my parentheses goes my x, the f function, which is 4x minus 3. Now we just have to simplify. On top here, since there's nothing connected to this set of parentheses by multiplication, they're not really serving any sort of purpose. So I'm going to ignore the parentheses and combine like terms, meaning that the positive 3 and the negative 3 up top are going to combine, canceling out, leaving me with 4x on top over my 4 that's on the bottom. Now on top here, everything is connected by multiplication. On the bottom, same thing. There's only the 4 though. Since there's a factor of 4 on the top and a factor of 4 on the bottom, we can cancel them out as well, leaving us with just x. And there we are. We have verified that both compositions equals x, and because both compositions equals x, the identity function, these two functions are indeed inverses of each other.